All right, welcome. Today we're looking at a concept that is honestly completely out there, and it could totally change how we think about exploring space. I want you to forget about giant rockets, forget about rigid metal boxes. We're talking about a spacecraft that's inspired by, well, spiders. So let's just start with the question right from the research paper itself, because it really nails the whole idea. For decades, right, space travel has been about building these armored tanks that can survive the harshness of space. This question flips that whole idea on its head. It asks, what if we built a craft that doesn't fight space, but actually feels it? Rides its currents, and basically becomes a part of that environment. And here's that contrast side by side. On the left, you've got the old way, the rigid bus. It uses brute force to get from point A to point B, pretty much treating space like this big, empty, hostile vacuum. But on the right, you've got this new idea, the spider craft. It's all about finesse and sensing. It engages with its environment, specifically something called dusty plasma. Just think of that as the invisible weather of space, a whole mix of charged particles, dust, and magnetic fields that are all around us. Now, this is where it gets really, really cool. Where did this inspiration even come from? Well, it turns out biology kind of solved a lot of these super complex engineering problems millions of years ago. So let's take a look at the high-tech toolkit that nature already built for us. First up, adhesion. How do you grab onto something in space without, a big claw? Well, just look at geckos and spiders. Their feet are covered in millions of these tiny branching hairs. This whole structure creates this incredibly powerful grip using something called van der Waals forces. But, and this is the key part, it's completely reversible. You can stick, and then you can unstick, on command. That is perfect for a craft that needs to both hold on tight and then let go and glide. And then there's the sensing. Spiders have these unbelievable hairs called trichobothria. They're so sensitive they can feel the tiniest puff of air. But what's even crazier is that they can detect weak electric fields. This is actually how some spiders balloon. They use static electricity in the atmosphere to fly for miles. Just imagine a spacecraft with hairs that could literally feel the plasma flows and electric fields all around it. And okay, this one is just wild. You know the amazing colors in peacock feathers? It's not pigment. It actually comes from their nanostructure. And researchers have figured out that you can use these structures to create tiny, tiny little lasers. For a microcraft like this, that could mean having patches on its surface that emit light to gently push or pull on tiny dust particles. And finally, how do you navigate? How do you find your way using something as invisible as a magnetic field? Well, nature has two amazing solutions. On one hand, you've got these little bacteria that build tiny chains of iron crystals inside themselves. They're basically perfect miniature compass needles. But then you have birds, which might use a super complex quantum process in their eyes to literally see magnetic fields. It just goes to show you, nature has both a simple and a high-tech solution for the exact same problem. So we have this incredible toolkit of biological systems, right? The obvious next question is, how do you actually piece all this together into a single working spacecraft? Let's take a look at the blueprint. So conceptually, it builds out something like this. First, you've got the spider-like legs and hairs. Those are going to be your main sensors and your grippers, using all those principles we just talked about. Second, you'd add those peacock laser patches for gently nudging the stuff in the environment around you. And third, right at the heart of it all, is the bionavigation core, the instinct of the craft, if you will, using those magnetic senses to find its way. Now, I want to be super clear about something. When we say bionavigation core, we don't necessarily mean launching a little container of living microbes into orbit. That's the wet biology approach over on the left, and yeah, that's really complex and fragile. What's way more realistic is what they call hard biomimicry. That means building tough, solid-state hardware, things like ferrofluidic chips and diamond sensors that perfectly mimics the physics of the biological systems but can actually, survive in space. Okay, so we have our craft, at least in concept. So where would it even go? What's the environment it's actually designed for? Let's look at what would be its natural habitat, the invisible architecture of space right around Earth. This craft is designed to navigate something called dusty flux rails. Now, these are not like solid highways in the sky. They're invisible flowing channels where magnetic fields and charged dust naturally form these pathways. A really good way to think about them is like the jet streams in our atmosphere. They're powerful, they're always shifting, and you can ride them to save a ton of energy, but only if you have the senses to find them first. And this shows so perfectly how the craft could operate in three different modes, kind of evolving over time. First, as a probe, it would just use its amazing sensors to map out these flex rails. That's actually a pretty near-term possibility. Then it could evolve into a surfer, where it would learn how to gently adjust itself to actually ride along them. And then, way out in the future, it could become a rider and could even mark these rails with some kind of pigment, creating pathways for other craft to follow. Pretty cool, right? So, how does it actually surf? This is probably my favorite part. It's called the dandelion strategy. Think about it. A dandelion seed has no engine. To travel for miles, it just uses its amazing shape to perfectly catch the wind. Well, this spacecraft would do the exact same thing. It would extend its legs or adjust its own electric charge to catch the natural solar wind and plasma flows, gently gliding along those cosmic currents instead of trying to blast its way through them. Okay, so this all sounds absolutely incredible. I know, almost like it's straight out of science fiction. And that brings us to the really big question. How real is any of this? So let's take a breath and do a quick reality check. First things first, we have to be really clear about where this idea stands. The Technology Readiness Level, or TRL, is a scale NASA uses. This whole concept is at a TRL of 1 to 2. That is the absolute bottom of the scale. We're talking about the earliest, most fundamental stage of research. This is a fascinating idea on paper, not a vehicle ready for a launch pad. This is really about planting a flag for a totally new way of thinking. But even as a concept, it's an idea that has a path forward. The paper doesn't just throw out a cool idea and leave it there. It actually proposes a series of concrete, testable experiments. The next steps are all about answering basic questions in a lab. Can these hair-like tethers actually sense plasma? Will that bionavigation core really respond to a magnetic field? Can those peacock patches actually move dust with light? Each one of these is a building block that has to be tested. And really, that brings us to the most important takeaway here. The real value of this whole Spidercraft idea isn't about promising some new kind of engine. It's about offering a completely new framework for how we explore space. It's about shifting our entire perspective from conquering the cosmos to understanding it, and maybe even cooperating with it. So I'll just leave you with this question to chew on. Is it possible that the next great leap in our journey to the stars won't come from bigger, more powerful rockets, but from the humility to learn the language of the universe? A language that, it turns out, tiny creatures on our own planet have been speaking all along. Something to think about. Thanks for tuning in.